Welcome to the next lecture on mathematical modeling. Last few classes we discussed about mathematical modeling of spring and damper. Today we shall discuss about how to model mass elements or inertia-like elements in the translational mechanical systems. As we have discussed earlier also, any of the translational mechanical systems can be modeled by using spring, damper, and mass. So, mass, when I say, it is not exactly the component having certain mass, but there are some inertia elements available in the system. All those inertia generating elements can be modeled as representative masses in the mathematical model. The mass as a building block exhibits the property that the bigger the mass, the greater the force required to get it a specific acceleration, isn't it? The relationship between the force and the acceleration A, as given by Newton's second law, is force is equal to mass into acceleration. So to accelerate a given mass, we need to apply some force. We call that force as accelerating force, and the mass in return generates some reactive force called as the inertia force, that is the resistance to the motion, isn't it? So that inertia force can be represented by using mass, where so F is equal to ma, where the constant of proportionality between the force and the acceleration is the constant called as mass m. Acceleration is the rate of change of velocity, that is dv by dt, and velocity v is the rate of change of displacement x. So v is dx by dt and a is dv by dt. So in turn, acceleration will be represented by d2x by dt squared, or in operator term, where capital D is equal to d by dt, the second derivative becomes d square. So thus, force is equal to mass into acceleration, that is equal to mass into dv by dt. Mass into dv by dt is given as d2x by dt squared. So d2 by dt squared is given by your operator d, so d square into x. So force is equal to mass m d square x, where d is equal to d by dt operator d. This is the representation, graphical representation. I show mass like this. I apply force F and it is accelerated. So change in displacement x, change in velocity, and then change in velocity, rate of change of velocity is acceleration. So by Newton's second law, force is equal to m into a, that is m d square x, where d is d by dt. F into, so what I do is I solve it for x. X will be equal to F into 1 by md squared, isn't it? So in the block diagram representation, if you recollect, we start from left hand side. These arrows represent the signals. I apply F as the input, force as the input, and I get X as the output, right? So that is the output side. Now, within this block, I write mass, and mathematically what I write is 1 upon md square, which is the transfer function of this inertia elements. So, how to read this block diagram? Inside the block, I have 1 by md square. I start from left. F into this 1 by md squared is equal to x. F into 1 by md squared. So F into 1 by md squared is equal to x. The transfer function, what is it? It is a ratio of output by input. What is the output? Output is x, input is f. So output transfer function, which is equal to output by input, which is equal to x by f, that is equal to 1 by md squared. So the transfer function for the mass is 1 by md squared. So translational mass is an inertia element. It is represented by this mass, or it's like a block m, and the forces are shown as arrow, and the displacements are also shown by arrow. Now what does this T indicate? Friends, this is the domain in which the force acts. If it is in the time domain, the force is a function of time t, then I write f of t, and displacement also, if it is function of time, I write x of t. Now what are the other options? If force is a function of derivative of time, d by dt, so I write f of capital D and x of capital D. If force is a function of let us say the Laplacian variable s. What is this s? If you recollect a Laplace transform, you must have studied. If it is function of s, the Laplacian function s, then I write f of s. Force is a function of s, and displacement also is a function of s. That we'll discuss when we derive equations for the entire system. So this is a time domain representation, and if it is f of s, x of s, it is Laplace domain representation. Plainly speaking, the arrows going shown like this are the forces, and the displacement is shown like this. So this is the representation of translational mass. A mechanical system without mass does not exist. If a force F is applied to a mass, if a force F is applied to a mass and it is displaced to x meters, then the relationship between force and displacement is given by Newton's second law. That is, F is equal to m into acceleration A, that is m into d2x by dt square, or d by dt is capital D, so d2x by dt square is d square x, so md square x. We have seen the transfer function also. Let us see few of the rotational mechanical elements, friends. Those we saw were translational mechanical elements. The logic remains the same. The Newton's laws only are used for modeling rotational mechanical elements also. So instead of linear spring, what I do is I show torsional spring. Now these are the torsional spring. You must have seen your cycle stand, you must have seen in watches, clocks, these torsional springs are used. Many of the shafts, these torsional springs are used. These also have stiffness, but that stiffness is called as torsional stiffness, K or K suffix T, KT. Let us say it's a free torsional spring having stiffness KT, torsional stiffness KT, and I have got two angular motions. There in linear springs we are showing displacement, linear displacement x. Now I'll be showing angular displacement theta 1 and theta 2. If I got both the angular displacements, then I'm applying a torque, and those are displaced by angle theta 1 and theta 2. This is the applied torque. That applied torque will also be in the same direction. It will not be linear, though it appears like that. No, it will be in the clockwise or anti-clockwise direction only. So the relationship remains the same. In the linear spring, we had seen force is proportional to x, and the constant of proportionality was k. So F was equal to kx. Now in torsional spring, instead of force, I'll be applying torque. Torque will be equal to stiffness, torsional stiffness kt, into, instead of x, I'll be having theta. Now here, difference between theta 1 and theta 2. What will be the effective angular displacement is theta 1 minus theta 2. So torque will be equal to k into theta 1 minus theta 2. If theta 2 is fixed, then it will be 0. Then torque T will be equal to k into theta 1. Then theta 1, if I solve it for theta 1, T into 1 by k will be equal to theta 1. I can draw the block diagram as I had drawn it for spring 1, isn't it? So this is the torsional spring, rotational spring or torsional spring we call it as. Then I have got, instead of damper, I have got torsional damper, right? A motor is shown like this, and it is provided lubrication. That is also providing the damping to the motion. Once again, in the linear damper, the damping force was proportional to velocity, linear velocity. Here, the damping torque will be proportional to angular velocity. Now, angular velocity is shown as theta 1 dot. The dot corresponds to d theta 1 by dt, or d theta by dt. That is shown as dot. D theta dot means d by dt of theta 1. If I use double dot, it will be d2 theta by dt square for angular acceleration. Okay. So here it is single dot, so it is d theta 1 by dt. So the damping torque is equal to torsional damping coefficient into relative angular velocity, right? So there it was, F was equal to C into V, linear velocity. So here it is C into angular velocity. If theta 2 is fixed, then I have got theta 2 is equal to 0, and what I get is damping torque T is equal to torsional damping coefficient into d of theta 1. And if I solve it for theta 1, it will be T into 1 by CD. So how do I write the block diagram for this torsional damper? Input will be torque T. I show an arrow. Input will be torque T. Block, rectangular box. Inside rectangular box, it will be 1 by CD, 1 upon CD, and output arrow will show theta 1, isn't it? So that is my block diagram representation for torsional damper or rotational damper. Like in the linear or translational mechanical system, we had mass. Here in rotational mechanical systems, instead of force F, I'll be having torque T, and instead of mass M, I'll be having mass moment of inertia J, isn't it? So in linear mass case, what was happening? I was applying force, and that mass was getting accelerated by amount A, that is d2x by dt squared, and the equation that I wrote for that mass was F was equal to mx double dot, or m into A, or m into d2x by dt squared, or m into capital D square x. Capital D corresponds to operator capital D, which is equal to d by dt. The second derivative is d square. So instead of mass, I'll be having mass moment of inertia. So any rotational component will be, the inertia components will be represented by the torsional mass or mass moment of inertia J. So that torque is equal to J into d2 theta by dt squared, J into alpha, J into acceleration. Like it was mass into acceleration in translational mechanical case, here it will be mass moment of inertia into angular acceleration alpha. That angular acceleration alpha is d2 theta by dt squared, or theta double dot. Theta double dot corresponds to d2 theta by dt square, or T is equal to J into, second derivative is represented by operator d square of theta. If I solve it for theta, it will be theta will be equal to T into 1 upon JD square. So how do I write the block diagram? From left hand side, I draw one arrow. What is the input? Torque T. So I'll be having a rectangular block. Inside the rectangular block, I'll be having 1 by JD squared, 1 upon JD square as the transfer function for this torsional inertia elements, and output arrow will be having theta. So this is what will be the block diagram representation of torsional mechanical element, that is mass moment of inertia or rotational mechanical. This is how instead of linear spring, linear damper and linear mass, I'll be replacing those by torsional spring, torsional damper, and torsional mass moment of inertia. So this is how I can model all the rotational mechanical elements. So mass moment of inertia I use. Let us see a simple mechanical system, simple translational mechanical system, how to build the equation of operation for such a simple translational mechanical system. Okay, friction is neglected here. Consider the following system. So how do I represent? I have a mass M, I have a spring K, and I am applying some force F, and I am getting output as displacement X. So this is one, let us say, a block representation, functional representation of some actual mechanical system, right? Actual mechanical system which is having a mass like this. Maybe if you take the case of a railway bogie, okay, railway bogie, and that railway bogie has got certain mass. let us say that the wheels are frictionless, just to assume. And then I have a coupler with a spring which is connected to the a fixed end, let us say, and I try to push that bogie uh, I push that bogie to move it away from that fixed end. So that bogie is represented by using such a mass, and the springs are there. In some cases, there will be some dampers also. In this problem, the damper is not considered. So friction is negligible. This is assumed. It's a simple case of spring mass system. And I'm applying some external force. So if such a problem is given, now I can show some hatching here to show the fixed head. Okay. So it's a spring mass system. So what is called as free body diagram? I draw one mass here. I draw one mass here showing this mass, and on this mass, what are the forces those are acting, friends? So the first force is external force F. Now I'm applying force F like this. Now how the spring would react when I'm trying to push that spring away? The spring will try to pull it back. The spring force will try to pull it back. So the spring force will be acting opposite to the action of external force. So the arrow is like this, isn't it? Fk, that is the spring force, it is in opposite direction. And then because of the application of force, this mass, if you remember, this mass will be accelerated, and that mass will provide me inertia force. That inertia force will be opposite to the accelerating force. If the accelerating force is acting like this, force F, the inertia force will be acting in the opposite direction. So F is in this direction, and inertia force and spring force are in the opposite direction, where Fk and Fm are force applied by the spring and inertial force respectively. So this is called as a free body diagram of this system, spring mass system. Okay, once I draw this free body diagram, it is easier for me to write the equation for this mechanical system, translational mechanical system. So I can have the convention F, external force F, is equal to the reacting forces, sum of the reacting forces. So external force F is equal to Fk, spring force, plus inertia force. So F is equal to spring force plus inertia force. Then now once I know these are the spring force and inertia force, now in the previous lectures we have seen how to represent the spring force. Spring force was represented by K into X, and inertia force was represented by M into acceleration. Acceleration is shown as x double dot or d2x by dt squared or d square x, isn't it? Then the differential equation of this system is F will be equal to, for inertia force, M into x double dot, that is M into d2x by dt squared, or mx double dot. This is the inertia force, plus spring force is Fk, K into x. So this is the differential equation for this spring mass system. How it is written? F is equal to M into d2x by dt squared plus kx. It's a second order time dependent linear differential equation with constant coefficients. Mass M and stiffness K are the constant coefficients. Taking the Laplace transform, now I convert. Now when I say F is equal to M into d2x by dt squared plus kx, so it is in the time domain, d2x by dt squared. It's a time domain. By taking the Laplace transform, I convert it into Laplace domain. Now why do I convert it into Laplace domain? If you recollect, to study a Laplace transform, time domain equation can be converted into Laplacian domain equation by using a variable s. Now what is the benefit? If I assume zero initial conditions, what happens is the differential equation gets converted into a simple algebraic equation in S, and it is always easier to solve an algebraic equation than a differential equation. So by converting the time domain differential equation into Laplacian domain equation, I simplify the method of solution of this differential equation. So taking the Laplace transform of both the sides and ignoring initial conditions, what I get is, instead of f of t, I get f of s. Now this f of t, the force being function of time, is converted into force is a function of Laplacian variable s, is equal to mass into, so d2x by dt squared. So it is md square x. It's a function of time domain. So I convert it into Laplacian variable s. So second order derivative is converted to second order variable in s. So d2x by dt square or d square x is converted into s square, right? Into x is a function of s. So it's just change of domain, time domain into Laplacian domain s. So ms square into xs plus, now instead of kx, what I do is k into x as a function of s. So x was a function of t earlier, now it has become x as a function of s. So by taking Laplace transform, I convert the time domain differential equation into Laplacian domain simple algebraic equation. Now what I do is I take out xs common, x as a function of s common. So I take x s common, and what remains is ms square plus kx bracket multiplied by ms square plus k, sorry, ms square plus k bracket multiplied by x of s. So what remains is fs is equal to into bracket ms square plus k bracket complete multiplied by x of s. Okay, then how is the transfer function written? Transfer function is the ratio of output by input. What is the output? X is the output. So xs is the output. So if I take the ratio xs upon fs, xs upon fs, what remains is on the left hand side, I have 1 upon this ms square plus k. So this is the transfer function of my simple spring mass system, friends. Okay. So this is how I get the transfer function of a given spring mass system. Let us take one more example. What I've done here. So spring was there, force was there, X was there. I have added the damper, right? Some lubricating element I have added. C is the damping coefficient. Let us draw the free body diagram. How it looks. Mass M. What are the forces? Forces acting like this. All these are remaining are the reacting forces. The spring force is Fk, damping force is also Fc, and inertia force is Fm. All these are acting in opposite direction to applied force F. So what will be the equation then? F will be equal to spring force Fk plus inertia force Fm plus damping force Fc. So F is equal to Fk plus Fm plus Fc. Now recollect, Fk is Kx, Fm is md square x, inertia force, plus Fc is Cdx, right? That is how I write the differential equation. The differential equation of this spring mass damper or spring mass dashpot system is F is equal to, this is the inertia force, M into x double dot, M into acceleration, or md square x plus c into velocity, that is cx dot, plus spring force is kx. So taking the Laplace transform of both the sides and ignoring initial conditions, what I get? I convert this time domain equation into Laplace domain equation. So f of it, here it was f of t, it is f of s now. F of s is equal to, so d square x will be converted into s square, right? And all these will be functions of s. So ms square into xs plus, so dx will be converted into sx as a function of s, and k will be converted to k into x will be converted into k into xs. All these are functions of s. I can take out xs common, x of s is common. What remains inside the bracket is f of s is equal to into bracket ms square plus cs plus k bracket complete, the entire bracket multiplied by xs. Now if I take the ratio for transfer function, I take the ratio of output by input. So xs upon fs will be equal to 1 upon ms square plus cs plus k. So this is the transfer function of this spring mass dashpot system. This is how we can derive the equation of motion, and then we can get the transfer function in Laplace domain of given spring mass dashpot system. Let us take one more example. Now this is as if it looks like a physical example, isn't it? I have shown one spring, I have shown one damper with damping coefficient, instead of C it is B. and it is applied with force F, and I have displacement X, right? So don't get confused. When I apply force F, how the mass is moving like this. Don't take it that way. This shows the positive sign of X. This mass will be moving in both the directions. It will be moving in this direction also, will be moving in this direction also. What this arrow says, treat this motion as positive motion, right? So, but actually is subjected to displacement in both the directions. Okay. So let us draw the free body diagram for this mechanical system. So this is mass M. Now mass M is acted upon by various forces. What are the forces? Force F, external force F, then spring force and damping force. Now how these forces will be acting? The spring force, when I try to just push this mass against the spring, what the spring will do? The spring will apply equal and opposite spring force on the mass. So the spring force will be opposite to the external force, opposite in direction. Similarly, the damping force, this force F will try to push this damper B in this direction, and damper B in return will apply the reacting force FB in the opposite direction. And when I try to push the mass in that direction, the inertia force will be acting in opposite direction. So when I draw the free body diagram, all the reacting forces will be having opposite signs or opposite directions to that of applied force F. Now I've just rearranged this block upside down. Okay. So if this is the external force that is acting, all the remaining forces will be in opposite directions. What are the remaining forces? Force offered by mass M, that is inertia force, will be acting in opposite direction to this external force Fm, external force F. And damping force will be the reacting force, that will also be in opposite direction to that of applied force, and the spring will also offer the reacting force Fk, which is acting in opposite direction to external force F. So I show the forces on the mass in this free body diagram: external force F and the reacting forces inertia force, damping force and spring force in opposite direction. Now how do I write the equation? External force F is equal to Fk plus Fm plus Fb, Fk plus Fm plus Fb. And how do I write the equation then? That will be equal to, I'll take the higher order derivative first, the inertia force. It will be md square x plus this will be bd into x plus k into x, isn't it? And that will be, if I convert it into Laplacian domain, how it will look? F of s will be equal to m into s square into x of s plus b into s into x of s plus k into x of s. If I take x of s common, what remains is f of s will be equal to into bracket ms square plus bs plus k bracket complete into xs. And if I take the transfer function, that is the ratio of output x upon input f, x of s upon f of s will be equal to 1 upon ms square plus bs plus k. So this is the transfer function of this spring mass dashpot system. Friends, this is how we can write the differential equation of operation for any of the translational mechanical systems and arrive at the transfer function. We can write the differential equation of operation, convert it into Laplacian domain, and find out the transfer function. Now, if I have got more number of masses, if I have got more number of springs, if I got more number of dampers arranged in different fashions, if I got a complicated system, I can always go in for another method of analysis called as grounded chair representation, which I'll post a separate video for this grounded chair representation, and how writing of differential equation of operations and obtaining the transfer function in a simplified way, I'll be discussing in that grounded chair representation method. I'll post that video in next class, and you can just go through that grounded chair representation as well. Probably compared to this method of analysis, this method of derivation of transfer function, that grounded chair representation is comparatively simpler. That I'll discuss in the next video. So thank you for watching. Thank you.